So we've seen how chemical reactions can be written in the form of chemical equations, and we know that we have to have the same number and type of atoms in the reactants and the products, but that they have swapped partners and are bonded differently. The law of conservation of mass does not allow matter to be created or destroyed. Here we're going to consider some other factors that chemists need to know about reactions. So we're calling this chemical reactions in the real world. Well, chemical equations tell us how chemical reactions could happen, but not always how they do happen. Sometimes we have side products form, and these are products that do not appear in the balanced equation but can form under different conditions. To perform a chemical reaction, we need more than just the balanced equation. We also need directions. This is like when you're following a recipe for a new culinary dish. It's not just enough to know that you need a certain amount of flour and sugar. The recipe usually gives directions as to how you should prepare the dish, how long and at what temperature to bake it at, etc. One of the things that chemists are interested in is the reaction progress. And that shows how a reaction progresses with time. Reaction energy diagrams, such as the ones shown on the right, basically track the energy in the reaction, with energy on the y-axis and reaction progress, which you can think of as being time, on the x-axis. You can see that the reactants have one energy and the products have a different energy. You can also see that in order to get from reactants at the beginning to products at the end of the reaction, there's an energy hill or barrier that needs to be crossed. And we'll talk about that in just a minute. So let's look closer at these reaction energy diagrams. If the reactants have lower energy than the products, this is termed an endothermic reaction. And an endothermic reaction is shown on the left-hand side of the panel below. If, however, reactants have higher energy than the products, this is an exothermic reaction, and this is shown on the right. You can see that products are lower than reactants. Now we can compare the two shapes of these curves. Endothermic on the left, products have higher energy than reactants, and exothermic on the right, where products have lower energy than reactants. Endothermic reactions require the input of energy for them to proceed for products. Exothermic reactions produce energy in the form of heat. So what sort of reactions are our combustion reactions? Such as the one shown that we have seen before. This is the reaction of propane with oxygen forming CO2 and water, and we know that it also produces heat energy. As heat energy is a product of the reaction, this is an exothermic reaction. So let's look at the activation energy. This is the energy hill in those reaction energy diagrams we just saw. There is an energy hill in all reactions, even those that are exothermic, the ones where heat is released. And this is the energy required to start a reaction. A good analogy is to think of a boulder at the top of a steep slope. Once the boulder is pushed, it will roll all the way down the hill, but it needs that initial push in order to get it going. Likewise, once propane is ignited with a spark, it will burn as long as there's still propane and oxygen available. An endothermic reaction, on the other hand, is like pushing that rock back up the hill. If you stop using energy to push the rock, then it's not going to continue going up the hill. And this is what an endothermic reaction is like. It needs a constant input of energy, and the initial push has to be greater than what is needed to keep it moving. The higher the hill, the slower the reaction. So reactions with big activation energies are going to be slower than reactions with small activation energies. And what about catalysts? Well, catalysts are materials that are added to chemical reactions to make them go faster. They do this by lowering the activation energy. And this can be seen by comparing the reaction energy diagrams below. On the left, there is no catalyst, and we can see that there is a high activation energy, a high energy hill to cross in order for reactants to go to products. On the right is the same reaction, and this is actually the rusting reaction, the metal iron being converted into iron oxide in the presence of oxygen. And on the right, we have this shown in the presence of a catalyst. The catalyst for this is actually salt. And what we see is that the energy hill is much lower once the catalyst is present. So it's a much lower energy hill when the catalyst is present. Lower activation energy gives a faster reaction. So catalysts make reactions faster. Another thing to note is that catalysts are not reactants or products. They're unchanged by the reaction. So an example of a catalyst would be salt that accelerates the rusting of steel. So cars rust faster in the presence of salt. So salt is a catalyst for the reaction, but salt is not considered either a reactant or a product. And finally, looking at a chemical reaction in the real world, if we consider heat packs that are used for athletic injuries, you get one of those heat packs that you put on your back or your shoulder if you've pulled a muscle. These actually use the rust reaction. And the rust reaction is shown. It is where iron reacts with oxygen to produce iron oxide and heat. It's an exothermic reaction. You can see that I have balanced the reaction here. So we have 4 iron atoms, 3 O2, 3 oxygen molecules, forming 2 molecules of iron oxide. It is balanced, and lots of heat, so it is exothermic. Now heat packs, shown here, actually have a fairly low energy hill. The activation energy is lowered because they contain a lot of salt. And as we saw before, salt is a catalyst for this rust reaction. So when there's plenty of catalyst present, it's going to make the reaction go fast, and that heat is going to be generated rapidly, which is why when you shake those heat packs, they very quickly start pumping out heat. So there's just a real live example of a reaction, an exothermic reaction, and the use of catalyst to make this reaction occur quicker.